Hello everyone. Let's go ahead and talk about the nuclear stability. Okay, why these elements undergo radiation, right? So there are two key factors determine the stability of a nuclide. What are those two factors? The first one is the number of neutrons n and the number of protons and their ratio n over z. Now you know inside the nucleus what we have is the protons and the neutrons, and depending on how many numbers they are and also their ratio n over z value determines whether it is stable or not. Let's talk more in detail in a little bit. And then the second one is the total mass of the nuclide. So if it has a higher mass, it would become unstable and it would start decaying by itself, emitting radiation. Okay. A plot of number of neutrons versus number of protons for all stable nuclides produces a band of stability, which is in the next slide, that gradually curves above the line for n equals 0. Sorry, n equals z. What is n and z here again? Neutrons and the protons. When they are equal, when the number of protons and the neutrons are equal, so then the ratio n over z would be 1. Okay, so this is the graph that I was talking about. So this line represents when the number of protons and the neutrons are equal. So the n over z equals 1. This side you can see protons and these are going to be your neutrons. And as it increases below 20, you can see it's according to the straight line. So n over z equals 1 below 20. 20 is the number of protons, right? So 20 element is calcium. So calcium and below we can see they are lighter nucleons and then they are stable. But as you increase the number of protons, what happens? As you increase, and you increase the number of neutrons also. So you can see that the n over z equals 1. This is that line, but the band of this is the band of stability. So the band of stability gradually curves away from the ratio n over z equals 1. But that doesn't mean all of these are unstable, but this is called band of stability. And in this stability band, if you expand this section over here, these black ones are your stable nuclides. And then the red ones and the blue ones, they are unstable. They would either undergo beta decay or alpha decay. These red ones alpha decay, and then the green ones positron emission or electron capture. Okay, and then you can see some of these black ones along the band of stability, they are stable. Some could be a little bit over 1, but they are still stable. But if you look here, if an element ratio n over z less than 1, they would be unstable. Okay, except hydrogen and helium. Lighter nuclides are stable when n equals z, as z means the number of proton increases. The n over z for stable nuclei gradually increases. As the number of proton increases, the ratio will become a little bit over 1. But there are some elements when their ratio is over 1 that they are still stable. Okay, all nuclides with z greater than 83, they are unstable. So remember this number 83. Any element with atomic number greater than 83 are unstable. Okay, so we talked about this graph. Stability and nuclear structure. Protons within the nucleus experience electrostatic repulsive forces, which destabilizes the nucleus. Now what do we have inside the nucleus? We have protons and neutrons. What's the charge of protons? 1. What's the charge? Charge is plus, right? The charge of the proton is plus. What is the charge of the neutrons? 0. So there are a bunch of positively charged elements, not elements, positively charged protons. Let's talk protons. Those protons are inside the nucleus. So what would you expect? They would repel each other. There is a repulsion between the protons because they are same charge, right? We know positive and negative attract. Negative, negative repel, positive, positive repel. Similarly, inside the nucleus also there are electrostatic repulsive forces. But then how they are going to be together inside the nucleus? There's another force that is called the strong force, which exists between all nucleons, and that counteracts the weaker repulsive forces between the like charges of positive. Okay, now this strong force that exists in all nucleons, that is 137 more stronger than the repulsive forces. So due to that, strong forces wins over electrostatic repulsive forces, and as a result we can see all the nucleons are bound together inside the nucleons even though they have positive charges. Okay, nucleons are found in nucleon energy levels. Okay, and pairing of the spins of like nucleons leads to greater stability. We have seen about the pairing of electrons. So similarly, nucleons also pair, and if they can pair, they have added stability. Elements with even protons usually have a larger number of stable nuclides. Over half the stable nuclides have both even number of neutrons and even number of protons. So if you have even numbers, you can see they pair like that. But if you have an odd number, you will end up having unpaired nucleons. So when you have even numbers, they are more stable compared to odd numbers. Number of stable nuclides were elements 48 to 54. You can see here cadmium atomic number 48, meaning it has 48 protons. So number of nuclides 8. Indium 49, odd atomic number, it has only 2. See the difference, 8 and 2. Again 50 has 10, 51 2. 52 8, 53 1, 54 9. So you can see the even numbered protons have more nuclides, stable ones, compared to the odd ones. Even odd breakdown of the stable nuclides, if you look at the number of protons and the number of neutrons, when both of these are even in a nucleus, the number of nuclides are 157. Even odd would be 53, odd even 50, and if both of these are odd, very small amount. Okay. Which of the following nuclides would you predict to be stable and which radioactive? Now we're gonna look at the ratio of N to Z ratio and see if they are 1. If they are 1, they are going to be stable. If they are less than 1, they are going to be unstable. If they are greater than 1, some could be stable, but some are going to be unstable. And another thing, if they are over 83 atomic number, they are going to be unstable. Now let's look at neon. 18, 10. So 10 here is the number of protons. 18 is the mass number, which is the sum of the protons and the neutrons. So the neutrons would be 18 minus 10, 8. So the ratio 8 over 10 would be 0.8. So as a result, neon would be unstable. In order to evaluate the stability of each nuclide, we determine the N and Z values. The N over Z ratio from A minus Z over Z and the value of Z. Then we compare the N over Z ratio with the stable values and note whether Z and N are even or odd. Okay, so the first one we talk about that already. N8, N over Z 0.8, which is too low to be stable. And then the second one, sulfur 32. Sulfur 32, here is the mass number, and the atomic number for sulfur is 16. So the number of protons 16, neutrons would be 32 minus 16, 16. So this nucleus has N and Z equal both 16. So N over Z ratio 1. So with atomic number less than 20 and even values for neutrons and the protons, nuclide is most likely to be stable. And then the thorium 236. So you locate thorium in your periodic table, and thorium atomic number is 90, right? 90 is greater than 83, so that is radioactive. And then barium 123. So you look up barium and then you find where it located in the periodic table. It is atomic number 56. If the atomic number protons 8 is barium 56. 56. So then the number of neutrons would be 123 minus 56. That would be 67. And then we're going to look at the N over Z ratio. 67 over 56 would be 1.2. For atomic number or the Z values 55 to 60, in the figure that we had seen in the band of stability, shows that between 55 to 60, in order for the atoms to be stable, N over Z value need to be either equal or greater than 1.3. But this one is only 1.2. So it needs to have more neutrons in order for it to be stable. So this nuclide has too few neutrons. That's why it's 1.2. So if it has more neutrons, so then N would be higher. And then N over Z can be greater than 1.3 in order to be stable. So as a result, barium 123 is radioactive. Now these radioactive elements undergo decay and become a stable element again. So let's look at how they are going to decay. What is the decay process? Now we can look up based on whether it has more neutrons or protons or the heavy nuclide to determine what is the mode of decay. If the nuclide type neutron rich, it has more neutron, and then it would end up having a high N over Z value ratio. So if that is the case, the mode of decay would be beta decay. Why? In the beta decay, neutron will turn to a proton. That lowers the number of neutrons over proton ratio. Okay, and if a nuclide is proton rich, it has more protons, so then you will end up having a low N over Z value. In that case, it would undergo beta emission or positron emission. Beta plus is a positron emission or electron capture. Because in this process, what happens is proton become a neutron and it increases the N over Z ratio. If you have a heavy nuclide, meaning atomic number greater than 83, that would undergo alpha decay. That reduces both atomic number, which is the number of protons, and the neutrons. Because alpha particle is 4 and 2. 4, 2, right? 4 the mass, 2 is the charge. Predict the nature of the nuclear changes each of the following radioactive nuclides is likely to undergo. Now we have boron 12, 5. What's the number of protons in boron? 5. What about the number of neutrons? 12 minus 5, 7. Right? Let's look at whether this one is proton rich or neutron rich. In order to do that, you need to locate boron in your periodic table and see what is its atomic number from the periodic table. You will see that is 10.8. But in this nuclide, boron is 12, right? Okay, let me explain you. If the nuclide is too heavy to be stable, Z greater than 83, it undergoes alpha decay, right? For the other cases, we use the Z values to obtain its atomic mass from the periodic table, just like I got the boron 10.81. If the mass number of the nuclide is much higher than the atomic mass, the nuclide has too many neutrons. Now the mass number given to us is 12. It is much higher than the atomic mass, which is going to be 10.81. The nuclide has too many neutrons. So in the boron has too many neutrons. N is too high and beta decay occurs. If the mass number is much lower than the atomic mass, which you find from the periodic table, the nuclide has too many protons. So Z is too high and the nuclide decay, positron emission, no electron capture. Now let's put that concept here. Boron has protons 5. Atomic mass, which you get from the periodic table, 10.81. The nuclide's A value of 12 that was given to us higher than its atomic mass. So it is neutron rich, right? So it will probably undergo beta decay. And then the second one, uranium 234, Z92. So if it is greater than 83, it will definitely undergo alpha decay. The third one, arsenic 81, atomic number 33. And you look up arsenic in your periodic table number 33, you will find 7492 is the atomic mass, 7492, and then you compare it with 81. Which one is bigger? The one that is given is bigger. Z doesn't change, 33. So meaning it has more neutrons. So the A value of 81 is much higher than the atomic mass. So it is neutron rich and will probably undergo beta decay. Sorry about that. Okay, similar to B. And then the last one, lanthanum 127, has Z 57. Right? Lanthanum is 57, and then you look up your periodic table and find the mass number 138.9. Which one is bigger, 127 or 138? 138.9 atomic mass is bigger than 127, meaning the A value of 127 is much lower than the atomic mass. So it is proton rich and will probably undergo beta emission or electron capture. That is how you're going to look at a given atom and decide whether it would undergo beta decay or alpha decay or would undergo beta emission or electron capture. Okay. So this graph shows us the uranium 238 decay series. Uranium is 92, pretty unstable, is greater than 83. So it will go through a series of decay until it reaches a stable nuclide. Now where does it end? It ends at lead. That's the daughter nuclide. A parent nuclide may undergo a series of decay steps before a stable daughter nuclide is formed. Detection and measurement of radioactivity. Now, how do we measure this radioactivity? There are two ways that we can do it. One method is ionization counter, and then the second one is scintillation counter. Ionization counter detects radioactive emissions as they ionize a gas. And then the ionization produces free electrons and gaseous cations, which are attracted to electrodes and produce an electric current, and then you can measure the electric current. That would give us how radioactive is the element of interest. In scintillation counter, it detects radioactive emissions by their ability to excite atoms and cause them to emit light. Radioactive particles strike a light-emitting substance which emits photons. The photons strike a cathode and produce an electric current. So based on that, we can find out what is the radioactivity. Now, what are the units of radioactivity? SI unit, and they are based on the people who found the radioactivity. Remember the Henry Becquerel and Marie Curie, they also won Nobel Prize for finding the radioactivity. The SI unit of radioactivity is the becquerel, defined as 1 disintegration per second. Curie is Ci, more commonly used. 1 Curie is this many disintegration per second. Rate of radioactive decay. Radioactive nuclei decay at a characteristic rate, regardless of the chemical substance in which they occur. The rate of radioactive decay, given the symbol A, also called the activity, is proportional to the number of nuclei present. A equals K times N. Now, the radioactive decay follows first order kinetics. I hope you guys remember when we study the kinetics, we learn about the first order, second order, zero order, right? So, radioactive decay follows first order. Excuse me. And the rate constant K is called the decay constant. The larger the value for K, higher the activity of the substance. Half-life of radioactive decay. Now this is a first order reaction, so we know how to find the half-life and how to calculate the half-life and what it means. But remind ourselves again, the half-life of a nuclide is the time taken for the half the nuclei in a sample to decay. The number of nuclei remaining is halved after each half-life. The mass of the parent nuclide decreases while the mass of the daughter nuclide increases. Activity is halved with each succeeding half-life. You can use this equation ln nt over n naught. N here represents the number of nuclides at a certain time, and this is 0 is at the beginning. K is a decay constant and this is the time it takes. Or we can rearrange this ln term to make it exponent. Nt equals n naught exponent negative kt. And the same ln expression, if you want to get rid of this negative, we simply can reverse this, flip this, ln n naught over nt equals kt. Okay, sometimes instead of n, we can also use A as the activity. A 0 over AT equals KT. Okay, because n is proportional to A. And this is the half-life graph. You can see at time 0 you have certain number of nucleons, and then when it reaches half-life, one half-life, you will have half of your initial amount, half of n naught. Another half-life, you have half of this amount, 1/4 from the initial amount. Go another half-life, you have half of this amount here, but 1/8 from there. And then the equation for the half-life is T half equals ln2 over K. I hope you guys remember this one from our kinetics chapter. Okay. Radioisotopic dating. What is radioisotopic dating? Normally, we use radioisotopes to determine the age of certain objects. Radiocarbon dating measures the relative amounts of carbon-14 and carbon-12 in materials of biological origin. Now, this ratio, carbon-12 to carbon-12, remain the same for all living organisms, including you and me. We do have carbon-14 in our body as well as 12, and this ratio remains the same. Once the organism dies, the amount of carbon-14 starts to decrease as it decays to form nitrogen-14. And we know that the carbon-14 decays at a predictable rate and it has a specific half-life. Measuring the amount present indicates the time that has passed since the organism died. Potassium-40 and argon-40 ratios also used to determine the age of certain rocks. Let's look at this example, how we can apply radiocarbon dating to find out the age of a bone. The charged bones of a sloth in a cave in Chile represent the earliest evidence of human presence at the southern tip of South America. A sample of the bone has a specific activity 5.22 disintegrations per minute per gram of carbon. Now the specific activity 5.22 for the dead one, the bone. And then the carbon-12, carbon-14 ratio for living organism results in a specific activity 15.3. This is the living one and this is the dead one. How old are the bones? Remember, they decay according to the first order kinetics. And then we are given the half-life of the bones are given as 5730 at the carbon half-life is this amount. We want to find out how old the bones are. Okay, what are we going to do? Since T half is given, we know K equals ln2 over T half. So we can calculate the K from the given half-life. Then use the first order rate equation to find the age of the bones using the given activities of the bones and of a living organism. See, K equals ln2 over T half. ln2, you can put this into your calculator and see what is ln2. 0.693 divided by the half-life, we can find out the decay constant. And we use the first order kinetics that we had seen in the previous slide. Time equals 1 over K ln A naught over AT. Remember I showed you over here? Ln A naught over AT equals KT. So if you want to find out the K, you simply take the T to the other side or you divide both sides by T. So here would be 1 over T for K. 1 over K ln A naught over AT. So 1 over decay constant. A naught is the living one and this is the dead one. Specific activity for the living organism 15.3, dead one 5.22, the bone. So this gives us the half-life, not the half-life, sorry, how old the bone is. 8,900 years old. Okay.